So welcome all the students to electrical machines course. So this course in fact I will teach up to mid semester. Okay, so whatever portion I think up to transformer I will teach. Okay, so then Professor Siva Subramani will start your lectures about DC machine, induction machine and synchronous machine. Okay. So this electrical machines is very important course because this is a foundational course, because if we'll see electrical machines are from very small size to very large size. They are being used in the industries. In small size we use in our laptop, in computer peripherals, in our home appliances, right? Like grinders and freezers. Everywhere we'll find the application of electrical machines. And there are also small machines which are being small motors are being used for robotic applications as well. So therefore this machine electrical machines course, that means it gives a foundational aspect to the electrical engineers specifically. So let us start with, so first of all I will just let you know how we'll evaluate this course, the course evaluation process. So in fact we have many components in this. So one is because your classes are going on online, so we are planning, these are the evaluation processes. So there will be real-time assessments and assignments, then some class performance. We'll see how you are doing in your class, and also please mute yourself. Somebody is unmuting, so please mute. Attendance required for attending the mid-sem and end-sem exam is 75%. That is mandatory. Okay. So, and the percentage of marks distribution is as per the Senate. As per the Senate guidelines, will let you know when the Senate will decide it, give its decision, and will circulate to you, and also will let you know. You also will be notified by the Senate. Okay. So this is the process of your course evaluation, and also be attentive and be always careful to attend the classes. It is very important. Okay. So now what are the contents we are going to cover in this course? First is your review of electric circuit theory. Already you have been taught in your basic electrical engineering, I think E101, where you are being taught about electrical circuit theory. So I'll just give a glimpse of it just to remind you how it works, and about the three-phase circuit, because three-phase circuit you have probably not have aware of much, so little bit I will give. And then we'll go for, please unmute. Then we'll go for review of basic laws of electromagnetism. Please mute yourself. Please mute. Then we'll go for review of basic laws of electromagnetism. So these laws are very important in fact in electrical machines, because electrical machines are, in fact it is based on this electromechanical principle, electromechanical energy conversion principle, which is in fact based on this electromagnetism. Okay, so how the electromagnetism plays an important role we'll see, and just I'll give the introduction of it, and again we'll see the principles of electromechanical energy conversion in this course, and then we'll talk about the transformers in detail very elaborately. I'll talk about the basic principles, constructional aspects, then the principle of operation, then the modeling, steady state modeling, equivalent circuit of transformer, then the performance equations, then we'll talk about the performance analysis using the equivalent circuits. Then I will talk about the three-phase transformers, then auto transformers. All these will be covered in the transformer. Okay. And then we'll talk about direct current generators, direct current motors. There are DC generators and DC motors. then your synchronous generators and synchronous motors, then obviously the polyphase induction motors. So these are the contents of your course. I will teach about this transformer, and this will be covered by Professor Siva Subramani. Okay. So let us first start with this review of electric circuit theory. So before we start, let me tell you about the different texts and references we use in this course. We can see here these books, these three books mostly will refer. There are many books you'll find in the market, also in curriculum. There are many books, but mostly will follow these three books: Electric Machinery by Charles Kingsley and Fitzgerald, and then Electric Machinery and Transformers by Guru and Hijiroglu, and then another is Electric Machinery Fundamentals by Stephen G. Chapman. Okay, so let us start with the introduction. We know that electricity in fact plays very important role in our life. So actually any is a very common medium of energy, because when we see for any kind of activity in our life, we depend on electricity in any kind of form. Like we need heat, we depend on electricity. We need coldness, we depend on electricity. We need light, we depend on electricity, right? So therefore electricity became very essential commodity in our life. So because why it is so? Because other forms of energy also available, and we can convert directly mechanical energy to other form of energy, to other form like light energy to some other form of energy. So there are interconversible phenomenon principles, but electricity is a common form of energy which is very common and which can be easily transportable and which can be easily used, right? And it is the most common energy we use, right, in our life. So therefore electricity plays in fact very important role, right? Now what you are seeing here in this picture, it is a power station, in fact thermal power station or natural gas station. Okay, and here we can see how the electricity is being generated. This is the generator here, right? Through the generator we produce the electricity, and it is being step up. The voltage is being step up by using the transformer, step up transformer, and it is being transmitted by the transmission line. This is your transmission tower, transmission line. It is transmitted to the consumers, those consume power, right, electricity. Now here but actually this generator is being run by this turbine. If we'll see, this is the turbine, steam turbine, and if we'll see, this turbine is getting energy from steam, and the steam is being generated by boiler. That means the steam is getting heat energy by burning the gas. Okay, so here in the boiler we are burning the gas, and therefore the steam is being heated and it is being fed to, it is being with high pressure, it is being injected to the turbine blades, and the turbine is being rotated, and that gives that, in fact here the heat energy is converted to the mechanical energy, and this mechanical energy is being again transmitted to the generator, and the generator produces energy. That means finally we are getting the conversion. Mechanical energy is being converted to the electrical energy. So this is electromechanical energy conversion, we call it, right? So this is electromechanical energy conversion. In fact the actual energy we are getting from this liquefied natural gas, right? That is naturally available natural gas, from that is the actual source of energy, and after being converted through many processes, finally it is converted to electricity, right? So this is a principle of thermal power station, right? And similarly also hydroelectricity, we can see hydro generation. Here the water is being injected through the penstock to the generator, right? Here the generator is vertically placed. Generally the hydro generators are vertically placed, and this is your turbine blade. And when the water is being injected, the generator rotates and it produces this electricity, right? We'll see how it produces electricity. In fact, this is the objective of this course. We'll see how the synchronous generators produce this three-phase power and it is being transmitted. Okay, and we'll study also transformer, right? And the generators, different types of generators, DC generators. There are different types of DC generators, and also synchronous generators we'll see, right? So there are many forms of conversion of energy to electricity, right? Here also we can see the nuclear elements like uranium fuel. It is acting as the fuel, and it in fact produces the steam, and that steam is being injected to the turbine, right? Then the generator produces electricity. So this is a nuclear plant, structure of nuclear plant, and this dome shape is known as the reactor, where the uranium is being used as the fuel to produce the steam through the heat energy, right? So this is how the nuclear power in fact is the electricity is being generated through the nuclear elements, right? So another form of energy conversion where we don't use the electromechanical energy conversion principle. All these three, if we'll see, this is thermal, hydel, and nuclear. All these three in fact consisting of the basic principle of electromechanical energy conversion, right? Here we can see we use a generator which converts the mechanical power to electrical power, and here also, right? But here we see this is the photovoltaic generation. It produces electricity but without any involvement of electromechanical energy conversion, right? So it produces directly the light energy. The photons are being directly converted to the electricity here, right? So this is another principle, right, which we will not cover in this course, right? And also we have seen wind turbine. This is also this also involves electromechanical energy conversion, principle of electromechanical energy conversion. Here the generator is being placed, right, in the wind turbine, and as the blade rotates, there are gear mechanism which rotates the generator and it produces electricity, and the electricity is being collected at the box connected at the terminal of the generator at the wind turbine station, right? So you can see here wind farm, there are many wind generators here, right? So this is how the generator, this is a motor. The structure of motor is given here. We can see here the motor is, the inside view of the motor is given. We can see here this is a squirrel cage type induction motor. You will be taught in this course there are different types of induction motors, squirrel cage type and wound rotor type. This is a squirrel cage type of induction motor which is very compact in design and which is very useful for industrial application. In many applications we see this kind of motors is being used, like in our fan, in a pump we use in a house. Most of the time we use this type of motor, squirrel cage of induction motor. And what we are seeing here is a transformer, right? So this transformer, we can see here, the purpose of transformer is not to convert one form of energy to other form of energy. What is the purpose of transformer? Transformer in fact it transforms the voltage level or current level of the electricity. It has a very special purpose of using in the electricity network, right? So also we have seen small transformer in your basic electrical lab. Also you might have seen a small transformers, right? 6 volt or 12 volt transformer which converts 230 volt to you have seen, right, 230 volt to 12 volt transformer, small transformer, ribbon type, and it is being used for electronic circuits. Okay, it is small, very small. But these transformers are generally known as distribution transformers or transmission type transformers, right? So they are step up, they are in fact operated in the very high voltage, in the kilovolts, like sometime it is being used for 400 kV to 132 kV, right? So this is a step down transformer, 400 kV to 400 kV is to 132 kV. Similarly, we have step up transformer at the generating end, which in fact we need to use to step up the voltage, because we need to transmit the power at a very high voltage, because in order to reduce the loss in the transmission line. So it is therefore it is important to step up the voltage. Generally the generators produce the power at 11 kV generally, most of the time. So this 11 kV is being stepped up to 400 kV, sometime 222 kV, right? So this must, because this higher voltage is essential to transmit the power, the bulk power, to the consumer end, because the generators are remotely located somewhere and we need to transmit this power to the consumers. So therefore the voltage need to be enhanced in order to reduce the loss, right? Because we'll know loss is I square R, right? So this current will reduce to when we are supplying a particular power, some certain amount of power, then if we'll increase the voltage, then this current level will decrease, right? So when the voltage level will increase, the current level will decrease, and therefore the loss will reduce, right? Okay, so the loss will reduce, and therefore it is essential to step up the voltages. So therefore transformer plays very essential role in electricity as a supply network. Okay, so we'll now talk about the course plan. So in this course we'll follow the steps how we can go for explanation and discussions, right? So for each machine we'll discuss the little bit about the constructional aspect, not elaborate design of the machine, because itself electrical machine design is itself another course, because it is not there in our syllabus. But we'll talk about little bit constructional features of these machines, not more detail, right? Not the design aspect. And then we'll talk about how the electromagnetic fields interact as a medium in the energy transfer process. So we'll see how these electromagnetic fields will interact and how the energy conversion takes place from mechanical to electrical, from electrical to mechanical, right? Because motor is used to convert electrical energy to mechanical energy, and generator is being used to convert mechanical energy to electrical energy, right? So those principles we'll discuss. Then we'll also represent these machines by its electrical equivalent circuit, and here we'll do only steady state analysis, right? So what is steady state analysis? I'll talk about only steady state analysis, not the dynamic analysis. We are not doing here the dynamic modeling of the machines or dynamic analysis of the machines. It is a different course itself, right? So therefore we'll talk about only the steady state analysis and also steady state performance of the machine. Then we'll talk about the performance using the basic laws of electric circuit theory. The basic laws of electric, like Ohm's law, Thevenin's law, right? Kirchhoff's voltage law, current law. By using those simple laws in the basic laws, we'll determine the performance of the machines and we'll evaluate it. Okay. So these are the steps by which we'll analyze every machine we'll talk about here, like your transformer, DC machines, AC machines, like induction motors and synchronous generators, all these things we'll talk only by considering these principles of explanation and discussion. Okay, now we'll talk about what is this steady state analysis means. Okay, so you can see here I'm showing you simple series RLC circuit, right, where you can see here the current is passing through this network, right, and here I have connected a DC voltage source. Okay, and now if I can write the equation for this this network, one is called steady state modeling. Directly I can write, if I'll apply the Kirchhoff's voltage law here, I can write V equal to what? Under steady state it will be, how much it will be? In fact, under steady state this capacitor will act as open circuit, so no current will flow, right? So therefore I will also become equal to 0 under steady state. But if I will connect this capacitance, because it is a DC source, right? Now if I'll connect this capacitance across here and I will make it short circuit, okay. Now if we'll write the equation for this, what I will write? V equal to IR, right? Because this inductance under steady state, when the DC source is connected, it will act as a short circuit, right? So therefore only the equation under steady state I can write is V equal to IR. Already these things you are being taught in your basic electrical engineering course, right? So now just I am removing this, and this is a series circuit, and I am replacing this source with a AC source. Okay, with an AC source I am replacing this. This now became VAC. Okay, so let us say this as Vm cos omega t. So this is an AC source. Now for this, if I'll write the steady state equation for this, how I'll write? I will write Vm cos omega t, I can write in the phasor form as Bm by root 2, which is RMS value, and the angle is 0 here because the phase angle is 0. You can write it is equal to IR plus then I can write it J of I omega L plus minus J of omega C into I, right, into I. I can write it as IR plus simply KVL, applying KVL I am writing these equations. This will be minus of J of omega C I. Okay, so this is under steady state. If I'll write this equation, it will look like this, right? Now if I'll consider, I'll consider this DC source, and I want to write the equation in the dynamic mode, right? Suppose there is a switch here, I'll connect a switch here, and this is open. Now the switch is closed at t equal to 0, and what will be the equation for current I can derive from this, right? Under transient condition, that means as soon as the switch is closed at t equal to 0. That is called dynamic modeling. Under dynamic modeling, if I'll write this equation, how it will look like? It will look like V equal to, I can write it as IR I is the instantaneous value, small I, plus L di by dt, right, and then across C the voltage will be Vc, right, and Vc is nothing but it is, I can write it as 1 by C I dt, right. So I can write the dynamic equation in this way, and this is called dynamic modeling. This is also we are applying KVL, but we are considering the transient condition under this in this circuit, right. So in this analysis particularly we will not cover this dynamic modeling aspect of the machines, electrical machines, because itself it is a different course, right? So therefore we'll only consider, we'll be only concerned about the steady state modeling. We'll write the equations, all the equations under steady state condition. We'll use the basic theorem of the circuit theory and we'll write the equations under steady state condition. Okay, we'll discuss like this. Okay, now this is your basics. So in order to comprehend the electric machines, we must be familiar with electromagnetic fields and be able to analyze the electric circuit. So therefore these two things are very important. One is electric circuit theory we must know, and electromagnetic fields. These two things we'll cover in these coming lectures, right? So now this is very simple circuit. Already you have studied these theorems, this Thevenin theorem, Norton theorem, then your maximum power transfer theorem. So this is a small problem. So this problem says determine the value of load resistance RL in the figure below for maximum power transfer. Okay, and we have to calculate the resistance RL by which we can transfer maximum power to this resistance RL. What is the maximum power delivered to the RL? We need to find the maximum power delivered to RL. So can you do very quickly and tell me the answer very quickly, please? Can you do it very quickly and answer it? Somebody has answered. Utkarsh Pathak 12 ohm, Rohan Kumar 12 ohm, Mayank Kumar 12 ohm. Very good. Okay. So very good. In fact, you have done this. So let us see how you did. So how you did this? Is just using the Thevenin theorem. We can find the Thevenin equivalent. We just remove this RL and find the Thevenin equivalent across A and B. So if we'll find the Thevenin equivalent and we'll find the Thevenin voltage across this, and if we'll reduce it, this network, to the Thevenin equivalent, so we'll find VTH, RTH, and here is your RL. This is AB, right? So this is your RL. Now you can easily find, so when RL will be equal to RTH, and under that condition your maximum power will flow to RL, right? So what is VTH? Can anybody tell? What is VTH? $45 volt. Okay, somebody told 45 volt. Utkarsh. Okay. So 45 volt. Now it is 45 volt is VTH, and RTH is also 12 ohm. So okay, it's easy because these are, if we'll open it and we'll find the Thevenin resistance, this becomes parallel, right? So it is, so your RTH will be equal to 20 into 30 by 20 plus 30, so it is around 600 by 50, so 12 ohm, right? And similarly you can find VTH applying KVL, right? So VTH is coming around, how much it is? 24 volt. how much he told? 45 volt. Okay, 45 volt, let us say 45 volt. So you can find it using KVL, so it is 45 volt. Now what will be the maximum power transfer? I will find. So maximum power transferred will be current. So your net current, it is I square RL, right? So that will be the maximum power. So I you can find VTH by twice of 12 ohm. So that is 24, right? So that means you can find, you can write 45 by 24 square into RL. RL is 12. So this is your maximum power transfer to this resistance. So many times we'll use also this maximum power transfer theorem in your machines course. So please be acquainted with this. Okay. Okay. So now we'll see, coming to the AC circuit analysis. So what you are seeing here is a sinusoidal wave, right? Sinusoidal signal. We can see here this is sinusoidal signal. If I'll write the equation for this, what will be the equation for this? The equation for this will be IT will be equal to how much? It will be Im cos of omega t, sorry, sine of, it will be sine of omega t plus theta. Okay, it is starting at the minus theta, so therefore it will be sine of omega t plus theta. Now if I will find the average value of this, how I will find the average value of this? I average will be how much? So for average value, what do we need to do? For average value we have a formula, that is 1 by t integration 0 to t ft dt, right? This is your this gives us the average value. Now if we will find the average value of this, obviously it will become 0, right? Okay. So therefore when any sinusoidal quantity, we will see the average value will be always 0. Now if we will find the RMS value, so if the RMS value is, the formula for RMS value is, RMS is your root mean square, right? Root mean square value. So RMS value, the formula is 1 by t 0 to t ft square dt square root. Therefore it is called root mean square, right? So we are taking a mean value of the square and taking the square of it. So root mean square. So root mean square of this will be so instead of ft you can write it here, right? So it. So here instead of ft you can write it. It is better. Okay. So now this will give us the RMS value, right? In fact, what this RMS value indicates? This RMS value indicates the equivalent DC quantity, right? Equivalent DC quantity means if I'll send this much of, suppose there is a resistance, right? And I am connecting a DC source here, right? Sorry. DC source here, and suppose 1 volt of DC source I am connecting here, and whatever amount of heat it will produce in this resistance, if I will replace this DC source with a AC source, suppose it produces 1 watt of heat. Now I am connecting AC source, so the AC source which will produce this 1 watt of heat in this resistance, that is known as the RMS value of this AC source. Okay, that means equivalent of the DC source, right? So that is called the RMS value of this AC source. Okay, so this is, I hope this is clear to you. Now we can see, sorry, this is overlapping. This in fact gives us the waveform of the RMS quantity. We can see here, right? So this is the RMS quantity. It gives the waveform of the I square t, and I will take the square root of it. It will give me the RMS value, right? Okay. So now we say that an alternating current has an effective value of 1 ampere when it produces. This 1 ampere is RMS value. Therefore, generally when we talk about this value of alternating current 1 ampere, 2 ampere or voltage 230 volt, these are all represent the RMS value of the alternating current, right? When it produces heat in a certain resistance at the same rate, that heat is produced in the same resistance by 1 ampere of the direct current. So that is called the RMS value of the alternating current. Note that the RMS value of a sinusoidal function is always 70.7% of its maximum value, right? So therefore we divide 1 by root 2. So 1 by root 2 is nothing but 0.707. So therefore the RMS value is in fact 70.7% of its maximum value, right? So that means if I'll write VRMS, I can write it as Vm by root 2, right? This is 0.707 Vm. So 70.7% of the maximum value. Okay, now we'll talk about the electric power. So in DC circuit, electric power is directly, we can write this as P equal to VI, voltage into current. That will give me the power, right, directly. But in case of AC circuit, how this power will find? So let us consider the instantaneous voltage and current and find the instantaneous power equation, and from that we'll find the average power. That is in fact, that will give me the actual power which is in fact useful, right? That is, we call it active power. Therefore we call it active power, right? So we can here we can see the waveforms of voltage and current and power, and how in fact this power is derived. We can see here this voltage is in fact written here Vt equal to Vm cos of omega t plus alpha, It equal to Im cos of omega t plus phi, right? Now if we'll write the equation for power, instantaneous power, let us say St. Okay, so this will give me Vt It, and if we'll multiply with the exact values Vm cos of omega t plus alpha into Im cos of omega t plus phi, right? And this I can write Vm Im half of cos of alpha minus phi plus cos of 2 omega t plus alpha plus phi. Just I am writing in terms of cos a minus b plus cos a plus b, right? So now I can write this as Vm Im by 2 cos of alpha minus phi plus cos of I just expand this. If I will expand this, it will give me alpha cos of 2 omega t into cos of alpha plus phi plus, sorry, minus sine of 2 omega t plus, sorry, into sine of alpha plus phi, right? Okay. So alpha plus phi is okay, keep it as it is in that form. What is in the previous form is there, we can keep it there. In that previous form is here cos of 2 omega t plus alpha plus phi. So this I can write Vm by root 2 into Im by root 2 cos of alpha minus phi plus Vm by root 2 Im by root 2 cos of 2 omega t plus alpha plus phi, right? Okay, so now from this equation, if we'll see this quantity, this is in fact it gives the average value of St. So if we'll find the S average, this is nothing but Vm by root 2 Im by root 2 cos of alpha minus phi. And this average power in fact gives us the active power or real power. We represent through this P, capital P, right? This is real power. And this component gives us the reactive power Q. Okay. So I can write this as Vm by root 2 is Vrms and Im by root 2 is Irms, right? So Vrms into Irms cos of alpha minus phi is what? Alpha minus phi is nothing but the phase difference between voltage and the current, right? So that I can write it as theta. So therefore I can write Vi cos theta is the active power, right? So that gives us the active power. So alpha phi, they are the phase angle of voltage and current. So therefore this alpha minus phi will give me nothing but the phase difference between voltage and current, right? So therefore the active power I can get from this equation is Vrms Irms cos theta, right? Okay. This is what here it is mentioned, P equal to half of Vm Im cos alpha minus phi, that is equal to Vi cos theta. Okay. So now let us do the phasor analysis, because phasor analysis in fact plays very important role in this course, because everything whatever we'll see, everything, all the analysis will be done through this phasor analysis. Okay. Now the AC signal whatever we see they are represented through this Vt equal to Vm cos of omega t plus theta. Now the question is how we can represent this signal in the phasor form. So how we can represent? Let us see that, right? So this is the signal available with us, that is Vt equal to Vm cos of omega t plus theta. So if I'll represent this in the exponential form, how I can write this? I can write this as a real part of, how I can write this? Because we know that the in the exponential form e to the power j of omega t plus theta, I can write it as cos of omega t plus theta plus j sine omega t plus theta, right? Now if I'll multiply here Vm, this will be also Vm, this will be also Vm, right? So now this Vm cos omega t plus theta, I can write it as a real part of Vm e to the power j omega t plus theta. Okay, it is fine, right? Now I can write this as real part of So Vm I can write it as root 2 Vrms, and I can expand this exponential term as e to the power j omega t into e to the power j theta. Okay. So out of this, if I'll plot this in the phasor form in the complex plane, that is, sorry, in the complex plane, if I'll plot it, this is real, this is imaginary. If I'll plot this, how it will look like? It will be having an angle of theta, and this is root 2 Vrms. Sorry. Okay. This is what it will look like, and this phasor. And because if I'll see with increase of time, as the time increases, this omega t will increase, and as omega t will increase, this phasor will also rotate, right? The angle will increase and this phasor will rotate. So this phasor will rotate at the speed of omega. So therefore no need to consider this omega t component, because with respect to time under steady state it is not required to consider this omega t, because it's a rotating phasor at a speed of omega. So we don't require this under steady state analysis condition. So therefore only we'll consider this angle theta, and important is Vrms. So therefore we'll drop from this root 2 and this part e to the power j omega t, right? So now your phasor, if we'll represent any signal, because these are common things, root 2 and e to the power j omega t, they're all common in all the signals. Only varying thing is Vrms and theta. If other signal, if we'll compare, these are the things we vary. Two signals if we'll see in the power system, right? So only two things, only magnitude of Vrms will change and this phase angle will change, right? So therefore the phasors are represented in terms of only in terms of Vrms and phase angle. Vrms and this phase angle, right? So therefore if we'll represent this signal in phasor form, I can write it as Vrms and the angle is theta. That I can write Vrms e to the power j of theta. So this is the phasor, right? This is phasor form. So any signal we can find it from its instantaneous form, from its time domain form in the phasor form, just by if we know the RMS value and the phase angle theta, right? Therefore we can write any signal in terms of, when we are writing it in the phasor form, we consider only RMS value and the phase angle, okay? So this is how we represent any signal in the phasor form. Okay, so this is all about, and now here we have different components in the circuit theory, or in any system in the electrical system, right? The resistance, inductance and capacitance. These are the basic elements in any electrical system, right? So if we'll write the equation in the time domain, so voltage current relationship will be VR equal to IR, and in the phasor domain it will be also VR IR, V equal to IR, but it is RMS value, VRMS and IRMS, right? Similarly for the inductance, if we'll see the voltage current relation in the time domain, VL will be LdI by dt, and in the phasor domain it will be j omega Li, that is nothing but IZL. Similarly in the capacitor, for the capacitor in the time domain, the current equation is C dVc by dt, or I can write simply Vc equal to 1 by C I dt, right? This is the relation. And your current in the phasor domain will be j omega c Vc, right? Okay, or I can write voltage is equal to I Zc. Okay, so Zc is nothing but this j omega c is the impedance, right? Okay, Zc is nothing but it will be minus of j omega c, because j will go to up. When it will go to our numerator, it will become negative. Okay. So if we'll draw the voltage and current phasors for each of the voltage and current for each of the elements, resistance, inductance and capacitance, how it will look like. For resistance, if I will plot the voltage and current, if I will take the voltage as the reference, then the current will also lie in the same phase with voltage, right? This is for resistance. And if I will plot this voltage and current phasor for inductance, if your voltage is here, right? So now where will be the current? Because it is j omega Li, so the angle will be how much? The current angle will be the current will be B by j omega L. So it is nothing but B by omega L, and the phasor will be minus 90. Okay. So that means your current is lagging voltage by 90 degree. That means for inductance, the current is lagging voltage by 90 degree, right? Similarly, if I'll plot this voltage of this current of this capacitance, how it will look like? If the voltage across this is for inductance. For capacitance, if I'll plot, then this is your voltage across the capacitance. This is okay. BR IR. Voltage across the capacitance. Now current across the capacitance will be how much? Your IC will be here. It will be j omega c Vc, right? So now if I'll plot this current, it will be 90 degree leading to Vc, right? So this is your current. So therefore for capacitive element, the current is leading to voltage by 90 degree. For inductive element, the current is lagging by 90 degree by the voltage, and for resistive element, the current is in phase with the voltage. So these are the basic idea for each of the element. When you will see in the network or during the analysis, we should consider like this. Okay. So this is how these are the phasor explanations. Now if we'll see the power diagram, if you'll see, the real power is obviously it is lying with the real axis because it is the active power, and the reactive power will be 90 degree leading to real power, and this is S is your apparent power, right? Apparent power. And when the S is defined numerically, you can see the equation will be Vi star, that is nothing but equal to P of P plus JQ, right? So this is how we find the, so if we'll take, suppose V equal to V RMS, suppose this is the RMS value, V RMS phasor, this is phasor, V RMS, the angle is, let us say, 0 degree, and I is, let us say, IRMS angle is minus theta. Let us say this is a inductive circuit. So theta is the lagging angle by the voltage, right? So now if I'll find the apparent power, that is nothing but Vi star I conjugate, that is I can write VRMS 0 into IRMS minus theta. So it will become BRMS IRMS minus theta. Sorry, minus theta will become plus theta when we take conjugate of this. Take it conjugate. Okay. Conjugate, then it will become plus theta. So it will become theta here, right? So that means Vi cos theta plus Vi sin theta. Okay. So Vi cos theta is your real power, and Vi sin theta, this is J, sorry, J of Vi sin theta is your reactive power. This is your real power, this is your reactive power. So as J of Vi sin theta is there, it is leading P by 90 degree. So Q is leading P by 90 degree. So therefore this is Vi sin theta. And the apparent power obviously is P plus JQ. That is nothing but the magnitude will be, if I'll find the magnitude, P square Q square square root. Okay. So this is how we find the power triangle. We call it power triangle. Okay. These are the basic analysis. Okay. So next class we'll see this problem. You have to do it because today we have time. So next class we'll continue with this problem. Okay. So thank you very much for your kind attention. Thanks a lot.